Well, thanks everyone for coming back. This is the last day of lectures. It's been a lot of fun. So let me at the end of last time, I was talking about these lattices, sublattices of the transcendental lattice of a K3 surface of index 2, and I was trying to show you how you could create like an honest K3 surface of degree 8 out of something like this. But time was running out, so I went a little fast. So I want to take one little step back and make sure that that example is definitely sort of seared in our brains. So I'll go over some of the stuff. It'll give me an opportunity to recap notation as well. So last time, okay. So I was looking at K3 surfaces, and I was working over the complex numbers. And in this case, the Brouwer group, we had sort of switched to an analytic version, and I sort of swept any comparisons under the rug. And I should say that the comparisons are not easy. It takes a lot of work. Let me just put the magic word gaga here and not say anything else. Okay. And we had this transcendental lattice of the K3 surface, which remember was the orthogonal complement of the Néron-Severi lattice inside H2 of xz, which is always isomorphic to 3 copies of the hyperbolic plane and 2 copies of the negative definite version of E8. Okay, and we saw that there was a one-to-one correspondence between cyclic subgroups of the Brouwer group of X of order n. And so first we saw surjections from the transcendental lattice to Z mod nz. And then, of course, by taking and cokernels, there's sublattices gamma inside Tx of index n and cyclic quotient. Okay, so this was some little cohomology calculation that we did. And so then, I forgot to start my timer again. Okay. And then we looked at a special case. And that special case was, so n equals 2. So we were going to look at subgroups of the Brouwer group of order 2. So there's sort of one non-trivial 2 torsion element in there. And so we're going to assume that the Picard group is pretty small. It's just Z, and this H squared was equal to 2. Question? And these were degree 2 K3 surfaces, and in this case we computed that the transcendental lattice was isomorphic to some vector V, which I'll spell out in a second, and then I had 2 copies of the hyperbolic plane and 2 copies of the negative definite version of E8, where, okay, so we called this lambda prime, and this V was equal to E minus F, and H was equal to E plus F, where, what are these E's and F's? So the first copy of the hyperbolic plane that seems to have disappeared here, so this was a basis for it, with Gram matrix 0, 1, 1, 0. Okay. So, and then we looked at the kernel of some surjections. So given this explicit description, you could just write down what surjections from the transcendental lattice to Z mod 2Z would have to look like. And so then we looked at the kernel of surjections like this. And what we saw was that there exist 3 possibilities for this kernel up to isometry. Okay, so this was a theorem that I attributed to Van Heyman during the last lecture. It's in this paper of his called Some Remarks on the Brauer Groups of K3 Surfaces. It's a real jewel. And the way that this up to isometry thing, we use some results of Nikulin that said that if I have these lattices that are even and indefinite and such that the number of generators that I need for the discriminant group is small compared to the rank of the lattice, then I can pin down the lattice by looking at the rank, the signature, and the discriminant form. So that was sort of the ingredient that went into seeing that there were only these three possibilities for these lattices. And at the end of last time, I actually looked at and started looking at an explicit example. Aha, this one also seems to be dying. Okay, so if you look at this lattice, I mean, there's sort of a pretty obvious sublattice of index 2 in here. Namely, I could take this gamma alpha, I mean, without looking at the surjection, just looking at a sublattice of index 2. Okay, that's a sublattice of index 2 in there. This lambda prime is nice and unimodular. And this, we saw this fell into the even case. So there were these three possibilities, and we divided them into two sets. One where the discriminant group was z mod 2z cubed, and the other one where the discriminant group was z mod 8z, and that one split up into an even and an odd case. And what I was saying at the end of last time is the following. So a little exercise. So this exercise is only going to work for the even case. Okay, and I'll explain why later. But this gamma alpha, this explicit one that I'm looking at here, can be primitively, and this is the key to the whole thing, re-embedded into the K3 lattice. Okay, so let me call this primitive re-embedding I. Okay, and the reason that this is good is, so on the other hand, so if I look at the H20 part of my original X, we know already that this is just a one-dimensional C-vector space, so let me call omega X a basis element in there. So what we know is that this omega X actually belongs to the transcendental lattice, at least after I tensor with C, almost by definition. I mean, this is orthogonal to the H11 bit, and Néron-Severi is in the H11. So, all right. Now, that means, though, because this gamma alpha is finite index, this vector is also in the scaled up version of my gamma alpha. And so now I have this embedding, I can look at its complexification. So I look at this C, and I look at the image of this line, and in the projectivization of, so this is inside as a point inside P of lambda K3 tensor C. But it's not just in this projectivization. I mean, this was the period point of my original K3 surface, and this is an embedding. So once I flush C omega X through I, it'll satisfy the same Hodge-Riemann relations. The square of this thing is going to be 0, and if I pair it with a complex conjugate, I'm going to get something greater than 0. So this actually will lie in the period domain. Okay? And so this is sort of amazing because now we can use the surjectivity of the period map to say the following thing. Let me over here. So there exists a K3 surface Y with whose period coincides with the period that I'm staring at. Okay, this is a different vector. We sort of re-embedded our lattice in this funny way. And so if you look back at the statement of the surjectivity of the period map, we can deduce from it that the transcendental lattice of Y is actually isometric to the image of this gamma alpha. And so, for example, here's, as a sanity check, this primitivity is really important because we saw yesterday that the transcendental lattice of a K3 surface better actually be primitive inside the H2. Okay, so I need this image to actually be primitive if there's ever a hope of something like this being true. And so what this means is that out of the pair, it consists of a K3 surface of degree 2 with narrow severity isomorphic to Z and an even class in the Brouwer of X2. Okay. Using surjectivity of the period map, we've come up with some degree 8 K3 surface that seems to be associated to this pair. Okay, so part of the reason this is nice is that, okay, what would be really nice, remember that at the end of the day, what were we trying to do? We're trying to understand what these transcendental elements of K3 surfaces were looking like, and we sort of appealed to the lattice theory to start studying them. And now, what I would really like is to have some, central simple algebra over the function field of X that represents this class. And the hope is going to be to sort of, instead of looking at the association that starts with a pair and produces this auxiliary variety, maybe we could try to go the other way. I could start with this auxiliary variety and produce this pair in a really explicit way. So the question that we're going to focus on is, can we go the other way? So it's a mystery. The answer is yes, no, maybe. The answer is Mukai. So Mukai, in the early 80s, gave us a way of going back, which is now sort of really nice, simple geometric interpretations that I'll tell you about later. But I will just say this because it's just a parenthetical remark. So what Mukai did is, he did a lot, but in the simplest case, his work showed that if you started with a K3 surface of degree 8, and if you considered a moduli space that parametrized stable sheaves, whatever those are, on this K3 surface that had certain fixed invariants, then this moduli space turned out to be a K3 surface of degree 2, and that was X. And then he tried to see this moduli space turned out to be a coarse moduli space. It was not fine, and there was an obstruction to the fineness of this moduli space, and that obstruction turned out to be exactly this alpha. Okay, so that was amazing. So he gave us sort of a way of going back, but it's a little abstract. If I give you sort of equations for the y, it's not so easy, sort of from that point of view, to sort of think of what the equations for the x and this and the alpha more precisely could be. It could be worked out from that, but I'll give you a sort of an easier geometric point of view. So that's, I want to actually do this, but before I do this, I want to go back and see, we only took one example here, and this was the even case. And there were 3 different isomorphism classes of lattices. So in some sense, we're sort of talking about one of these. What about the other 2? Okay, what's going on there? So before we try to go back the other way, so first, so what about the other isomorphism classes?
There's like some point I'm just not getting to, but why should we take the isomorphism class of the lattice as an abstract lattice as supporting? Because it depends a lot on the embedding. Are you claiming that like any 2 guys in this even class are related by a monomorphism with the big lattice?
No, but let's talk about that later. Okay. Please, yes, okay, great. So, all right. Okay, so let me tell you what the other two isomorphism classes sort of seem to give us. So, all right. So I'm going to start with, so again, x is a K3 over the complex numbers. The Néron severity of x is going to be just a ZH. H squared is going to be 2. And then this gamma alpha was one of these three things that I was looking at. So the kernel of some surjection from the transcendental lattice to Z mod 2Z. Okay? And then, so the first thing is, so let's look at the case where the discriminant group was isomorphic to Z mod 2Z cubed. Okay, so then what? Okay, I mean, what sort of thing are we really looking for? So what happened in the even case? In the even case, this sublattice of index 2 turned out to be the transcendental lattice of something else, some other variety. So what I'm hoping here is to sort of tell you that the transcendental, that this sublattice of index 2 looks like the transcendental cohomology of something else. Okay, so indeed, so you might have to switch the sign of the bilinear form to do this. This is a minor technical thing. This ends up being, so I'll write it down and then I'll explain in detail. So the perp, so there's some fourfold y, okay, and this is supposed to be sort of my algebraic codimension 2 cycles, and then I'm taking the orthogonal complement. So this is sort of the transcendental cohomology of some fourfold y. And now let me tell you what the y is. So where y is a 2-to-1 cover of P2 cross P2. Okay, and I have these projections. Now this 2-to-1 cover is going to be branched along a type 2-2 divisor. Okay, and I'll have my projections. Let's call them pi 1 and pi 2. And these h's, this hi, is what happens when I pull back the class of a line in P2. So when I pull back the class of a line here, I'll get some codimension 2 cycle in y. And so I can create this. I know that I at least have this much in the algebraic part of H4. And there should be nothing else, in fact. So this should be viewed as sort of a similar statement to the one for the even class. Let me make the one for the even class so it becomes a little clearer. So 2. So if gamma alpha belongs to the even class, this was where the discriminant group was Z mod 8Z, then in fact this gamma alpha was isomorphic to the transcendental lattice Ty of some y a K3 surface of degree 8. So this was the example that we just saw. Okay, and we should sort of view this first thing as a similar statement. We're saying that my sublattice of index 2 up to some sign is actually looks like the transcendental cohomology of some other variety. And there was the odd class as well. And if I'm in the odd class, so then this statement is going to be similar to the first one. I might have to switch, take care of a sign there, some weights, and this is going to be the transcendental cohomology of a cubic fourfold that contains a plane. So let me write this down. So y in P5 is a cubic fourfold that contains a plane P. And H is the restriction of the hyperplane class. So these came up yesterday in Ravi's lecture. I mean, rationality of these of cubic fourfold is sort of a huge question. So sort of most cubic fourfolds in an appropriate moduli theoretic sense, when you look at their middle cohomology, the only algebraic class that you'll see is the square of the hyperplane class. And so when there's an extra surface in there, they're called special cubic fourfolds. And these are some of the simplest special cubic fourfolds that are out there. Now, the point of what I'm trying to tell you with this theorem is that this sort of association that so far is a little bit vague between a K3 of degree 2 plus a Brouwer class and some auxiliary variety happens no matter what the class of the isomorphism class of the lattice is. So let me say that. So you get this sort of association between the pair x comma alpha and y always. Okay, so now there's a thing though, I mean, how do you prove something like this? So let me just say the proof. I guess I should write here for the benefit of posterity. The proof is one word, it's Nikulin, so today's name day. Okay, so what do I mean by that? Well, to prove the actual statement that I just gave you, all you really have to do is sort of know what these lattices look like. And I mean, if I want to say that these two lattices are isometric, then I just pull out that Nikulin trick of saying, oh, well, their rank, their signature, and the discriminant form are the same, and so they must be isometric. For that, of course, one has to understand a little bit what this H4 looks like. And so this H4 looks way different than the H2 for a K3 surface. It's got plus 1 to the 21, and then minus 1 to the 2. But once I look at this lattice in here and I take the orthogonal complement, out pops out, a couple of copies of E8 and a couple of hyperbolic planes, and then you really start seeing that maybe there's a chance. But the proof, as the way I wrote it here, and I'm pointing to Nikulin, is just lattice theory. This, for all we know at this point, if we're just using the lattice theory, this could just be a numerical coincidence. Okay. Now, we've seen, using the surjectivity of the period map, that it was not really a numerical coincidence in case 2. There was like a flesh and bones, flesh and blood. I should have looked that up. There's like a real-life K3 surface of degree 8 that comes out of a K3 of degree 2 plus an even class. Okay, now, we don't have surjectivity of the period map for, say, cubic fourfolds, although we do understand the image of the period map thanks to work of Laza and Loyenha. So you could still work that way and try to produce a cubic fourfold that contains a plane that exists in real life. But instead, let me sort of show you a different take on it. So where is the geometry? The lattice theory was beautiful. The geometry in the case of K3 surfaces is there, but so the idea. What I'm about to say now, no, it's sort of independent of the proof. So.
How does that proof work? Like, you get the lattice, but you don't have surjectivity of the period map. Where's the y?
Yeah, exactly. No, I mean, but you understand the image of the period map, and in this case you can produce a y, but actually for the other one, the period map is not being studied really. So for example, it'd be nice if someone actually went out there, and proved a good statement for those things. So somehow, this is part of what this theorem is trying to tell you is people should study this and the moduli spaces of such things and try to see, there is some recent work by a few people, Manivel included, that sort of starts to address this kind of issue. But there's definitely interesting mathematics to be done here. And this, when Brendan Hassett and I started working on these things, that was not available. And so we were just sort of, tried to come up with some idea to actually create the Y and some correspondence that would actually show a nice isomorphism of these lattices. So the idea is to use this auxiliary variety. So So I'm going to go the other way. I'm going to start with the y, and I'm going to create the pair x comma alpha now. So use this auxiliary variety to construct a bundle of quadrics. So y prime to p2. Okay, so so e.g., in the case that you have a cubic fourfold containing a plane, what I do is I just blow up that plane. And so I have a map to y. Now I can also project away from the plane. This is my y, remember, is in P5. So if I project away from a plane, I should land in a P2. Project away from P, and so now I'll actually get a morphism here, and so this is going to be my y prime. And if you sort of think about what this map is concretely in terms of equations, this is actually a bundle of surfaces. And what I'm claiming here is that in all three cases, you can do something like this. You start with your y, cubic fourfold containing a plane, and you can produce a bundle of quadrics. The other cases, one of them is actually quite easy. So we had this double cover of P2 cross P2. Just take the projection to P2, pi1 or pi2. That's actually already a bundle of quadrics because the branch locus is a type 2-2 divisor. Okay, so, and the last case is a little bit more complicated. It involves the net of quadrics that Várilly mentioned in her lecture yesterday, associated to a K3 surface of degree 8. But one example should suffice to sort of show us what the picture is. And in the lecture notes, I actually explained the other two. And now let me draw you my favorite picture. Okay, so let's see. So this is going to be my bundle of quadrics. And it's a four-dimensional thing. So let me draw it like that. This is y prime. And so some of my quadrics are going to be nice and smooth. And I should say that, I mean, this picture is kind of a cartoon sketch, but sort of. I mean, this y prime that I just concocted for you, I mean, this is a four-dimensional thing, and so the fibers above some point of P2 are two-dimensional. So really, you know, they do look a bit like this. And then every now and then you'll get some degeneracy. And you sort of want, I'm hiding away that I don't want the degeneracy to be too bad. Okay, and so what am I going to do here? So I have my map to P2. And so now, some of these quadrics, these will map to some random point in here. But then, every now and then, you know, you're going to have the locus in P2 where the fibers are singular. And if you look at the actual equations of what's going on, that locus is going to be a sextic on P2. And so this is starting to smell right. Okay, so let's do another color. Okay, so I've got this. So let me put this in green. Okay, now this looks a bit, I mean, it looks like we already have a K3 surface of degree 2 here out of this bundle of quadrics, sort of, right? What we really have is the sextic curve. What I need is a double cover of P2 that is branched along this thing. And as a geometer, you think, okay, I'm done. But if you're going to do arithmetic and keep track of fields, then taking this double cover might involve some twist. And how do you know which twist you're supposed to take? So, well, the reason is that this picture is incomplete. As you can see, the left-hand side is empty. We need to do a little bit more work because I don't just want to produce the K3 surface. I want to produce the Brouwer class, and I want to see it geometrically. Okay, so the key here is we're going to look at big blob. So this is going to be W. And this is, okay, it has a scary name, but I'll parse it out. This is the relative variety of maximal isotropic subspaces. Whoa. And what I mean by that, okay, so let's look at sort of one fiber at a time. There's quadrics in here. And inside quadrics, you're going to have these maximal linear subspaces that depend a little bit on the dimension of a quadric. For a two-dimensional quadric, we're talking about lines. So this horrible thing here is supposed to be parametrizing the lines in the fibers of my quadric. So let's think about what that looks like. So if I have a smooth fiber, this is literally a P1 cross P1. Remember this Y prime was a fourfold. And in P1 cross P1, there's sort of two rulings. Okay? And so to each one of these lines, I want there to be a point there. So this variety is parametrizing the line. So one point in here is a whole line in here. And now in each direction, there's a P1's worth of lines. And there's two families, there's two directions that I can go in. Okay, so for a single one of these fibers, I'm supposed to see two conics inside my W. And then I will also have, now, when the quadric degenerates, then I lose one of the two rulings. They sort of collapse on each other. And so this time, I'll still see some points here, but there's only going to be a P1's worth of points. Okay? And sort of, you can think of it, you know, it's a little movie. As I sort of move from here to here, these two things are collapsing into one thing. And then the magic word is Stein factorization. So there's no map from here to Y prime, but there is a map to P2. Okay, I mean, I take, you know, this point. I know that the point is supposed to say something about this fiber, so I send it here. Okay, so I look at Stein factorization. What is that? Well, there's going to be some blob. Okay, and I'm going to call this X for sentimental reasons. And now Stein factorization has this first part that has connected fibers and then some finite part. And if you think about what the Stein factorization will look like, well, this whole conic is going to collapse to a point, and that one's going to collapse to a point. And then this conic is going to collapse to a point. And the other map is going to be my finite map. These 2 points are going to go to this red point, and this green point is going to go to that one. So what on earth do we have? We have a double cover of P2 that's branched along the sextic curve on my P2. That's the K3, right there, geometrically. I mean, live, you know, not lattices. This is the K3. Okay, great. But then we have this other junk here. What is that? That is the Brouwer class. We win. So this to X is alpha. Okay, and what do I mean by that? Okay, well, so, I mean, take a look. So the generic fiber of this thing is a conic. Right? Okay, a conic, as we've seen in previous lectures earlier this week, is, I can turn it into a quaternion algebra, right? Ax squared plus by squared equals z squared, turned into a comma b as my quaternion algebra. And this quaternion algebra is going to live over the function field of x. And that's my Brouwer class. So really, if I write down some equations for a cubic fourfold that contains a plane, and I just start writing down equations for these things, it takes a while to write equations for this, but you can, then I really can write down the generic fiber, the conic, and just write a quaternion algebra over the function field of x. And this is going to be my transcendental class. Well, okay, good. And, okay, we did this all over the complex numbers, but now that we look at the geometry of it, it doesn't really, I can do all these things. If my starting data lives over a number field, then all of these things can be done over the same number field. And so I'll end up with a class that is actually not just some abstract transcendental class, but it'll live over the number field. Okay, so that's the picture. Now, in the other cases, in the double covers of P2 cross P2, it's the same picture here. In the case, in the K3 of degree 8 to degree 2, things are a little bit more complicated because this space here is actually not 4-dimensional, but 6-dimensional. And so the quadrics have much higher rank, and so these maximal isotropic subspaces are not lines, but they're P3s, and so this W is a lot more complicated, and it takes yeah. So but the spirit of the picture is still correct. So I should say that so Brendan Hassett and I, well, it seems like eons ago now, but came out in print a couple of years ago, used this circle of ideas to actually write down a concrete K3 surface over Q of degree 2, whose Néron severity group is isomorphic to Z. And how do we prove this? We used all of the stuff from lecture 2 to do this, with some transcendental 2-torsion-Brouwer element, so transcendental, such that there are local points, but this class actually obstructs the Hasse principle. So transcendental classes of the Brouwer group can get on in the way of the Hasse principle. That was sort of the moral of the story, and so there had been some previous work on these things, but often the construction of the transcendental classes would involve things like elliptic fibrations, and somehow the nature of the construction is also required that the x that you started with had rational points, and so what that meant was that people could produce transcendental classes, but they would only obstruct weak approximation at best because your surface already had points. And so what we set out to do was to try to do the Hasse principle, but also to, giving ourselves this hypothesis of Picard rank 1 would mean that you would have no extra structures that you could sort of cling on to try to produce classes. And so this would have to really work in some nice level of generality. So that was nice. And I should say that once you have this alpha as a quaternion algebra over the function field of your K3 surface, doing this sort of computation is a standard thing. It's hard, it takes a lot of work, but you can sort of turn the handle, and you have to have a lot of patience, and you probably have to try 10 different surfaces sometimes to get it to work, but it can be done. Now, what I want to do, as I'm trying to finish up, is to tell you a little bit about morally what's going on. Because Arnav's point as well about, okay, what is this lattice stuff? What is it really trying to tell us? It's a shadow of something. And so morally, here's what is really going on. So this is going to be the moduli of K3s of degree 2. You can use the period domain to try to build some coarse moduli space. You'll have to mod out by some orthogonal group, and it's complicated. Let's not get into that. And what I want up here, which is not really defined in the literature, so there's some sort of moduli with a little bit of level structure. So I want a K3 surface of degree 2 together with one of these cyclic subgroups of order 2 in the Brouwer group. And what this lattice theory and this geometry is really trying to tell us is that this moduli space, if you write it down, if someone ever writes it down, so it has 3 components, and the first component is K3 surfaces of degree 8. The second component is these special cubic fourfolds that contain a plane. They have discriminant 8. And the third component is going to be this double covers of P2 cross P2 ramified, branched over a type 2-2 divisor. And in fact, we even know what the degrees of these things are. Those should really correspond, in a sense, to the number of isomorphism classes that we saw. So I think these were 2 to the 20 minus 1, and this was 2 to the 9 times 2 to the 10 plus 1, and this was 2 to the 9 times 2 to the 10 minus 1. Okay? And now I should say, okay, that formally this space has not really been defined. I don't think, so it shouldn't be so hard to do it, say, over the complex numbers. It'd be nice to actually have this over number fields. Really sort of do this properly with moduli functors and set this whole thing up over number fields. That's not done. over the complex numbers, you can actually write down maps from these spaces to this one, okay, and prove that they have these degrees. And it essentially it'll boil down to the lattice calculation that we just did. But this is sort of what's going on. And so this sort of prompts a whole slew of questions. So, okay, what about other elements? I mean, and what about degree not 2? I mean, we focused on 2 torsion and degree 2 K3 surfaces, but what happens if you keep going? So what about other elements in Burr X? And so I should say, time is a little short, so so Yeronimou and Skorobogatov have figured out what, for example, the odd part, diagonal cortex. I should also put Zarhin here. So in a series of papers, they've sort of really pinned down what the Brauer group of diagonal cortex can look like. And for example, for the transcendental odd torsion, there can be a Z mod 3Z and there can be a Z mod 5Z and there can't be anything else. So over an algebraic closure, you know that there's Z mod 7Z squared worth of stuff because these things have Picard rank 20. But none of that actually descends to the ground field. So there's some really interesting recent work. This was published in 2015. There's also a very nice theorem of Rachel Newton, who's here, and so you should ask her all about this. It's really cool. It's fresh off the press. So if you take an elliptic curve with, say, I'm going to say full CM, so CM by the ring of integers of an imaginary quadratic field, and you look at the Kummer surface that comes out of this elliptic curve, and if I suppose that the Brauer group, so let's look at odd torsion of the Brauer group, of the transcendental Brauer group. So we've been looking at things like 2 torsion. Let's look at some odd torsion. Let's suppose that this is not 0. Then in fact, 2 things happen. So this is quite nice. First of all, there's no algebraic Brauer group. The algebraic Brauer group is just the constant algebras. And the full Brauer group, or the quotient that actually matters, is Z mod 3Z. And she has an explicit description of this element that allows her to prove the following statement. If you look at the Brauer set of this Kummer surface, it's strictly contained inside the set of local points. So there are always obstructions to a weak approximation on these things. So I sort of gave Kummer surfaces the short, I forget what the idiom is. So I didn't say much about Kummer surfaces, but they're an incredible testing ground. They're beautiful. They have tons of structure, and look at the sort of theorems that come out. E is an elliptic curve, so it has points. So X has points. So the Hasse principle is not at stake here, but you could try to do something like this for twists of objects like this and try to prove a similar theorem. So that's and it's to this day there's not an example of a K3 surface that fails to have points because of an odd order element in the Brauer group. So that's something that also is, people have been wondering if that's just can't happen, for example. And so this is sort of in one direction. What about other elements? If I sort of go back to the to this lattice business, then you can sort of push the lattice. I mean, I took the simplest example, but you can imagine that I now start taking a K3 of some other degree, and I look at, say, P torsion or N torsion, and I play the same game with lattices that I did, and okay, what comes out? And so let me give you a theorem by way of a picture. Okay, so P is going to be, I'm going to study P torsion on a K3 surface, so X is going to be K3 over C of degree, so Néron-Severi is going to be ZH, H squared is going to be 2D, and P is going to be a prime not dividing D. And I should say all of this is joint with McKinney, Kelly McKinney, and Justin Sawan, Sho Tanimoto, and myself, in 2014. It's sort of a jazzed up version of lattice computation that I showed you last time. It's a lot more involved to actually get a result, but in the end, the result is very similar. So we're going to have this coarse moduli space of K3 surfaces of degree 2D, and there's going to be three components in the moduli space with some level structure coming from a cyclic subgroup of order P inside the Brouwer group. And we can calculate the degrees of these maps. Okay, and they're going to generalize the case of P equals 2. So this is P to the 10, P to the 10 plus 1, and then 1/2 P to the 10, P to the 10 minus 1, and then P to the 20 minus 1 over P minus 1. Okay, and in fact, so you can use, I had mentioned Mukai before. Mukai did something way more general, and if you look at what he did, then it's not so hard to identify one of these components already as K3s of degrees 2dp squared. This is what happened also when P equals 2. When P equals 2 and D was 1, I had K of 2 here and K of 8 here. So this is sort of what happens in the more general case. We can't say a whole lot. So for the other two components, if I do limit myself to D equals 1, but I look at other primes and P is 2 mod 3, this turns out to be special cubic fourfolds of degree of discriminant 2P squared. So they appear again. When P is 1 mod 3, you also see CO2 of P squared, but these two things actually collapse on each other. And this is something that Brendan Hassett 15 years ago had called a K3 associated to a special cubic fourfold. There's still three components, it's just that these two descriptions actually describe the same component. And then this one, okay, if you could tell me what it is, I'd really appreciate it. That would be awesome. So there's some work to be done there. Now, this is coming from the lattice theory. So what we did is sort of a very drawn out lattice calculation that took a while, and then with these discriminant groups and so on and so forth, we can write down maps between this moduli space and this moduli space. That was known well before. This was also known well before. So there's actual maps from these moduli spaces here. This moduli space, as K3s of degree 2 with some level structure, has not really been set up. And I would like it to see set up over number fields and sort of really see that this picture that I'm drawing for you is something that actually happens in real life over number fields. That'd be awesome. So this is the sort of thing that's going to tell us where transcendental elements are supposed to come from. And in fact, this picture suggests the following challenge. Okay, so let me take P equals 3, and D is 1. P equals 3. And then look at this divisor, C18, so 2 times 3 squared. So these are cubic fourfolds with a Del Pezzo surface of degree 6 contained inside them. So they have a surface, it's not a plane this time, it's something a little more complicated. Okay, and so the question is, okay, where's that picture? What's this picture in that case? Okay. So the challenge is to produce out of this data a K3 surface of degree 2 with a non-zero 3-torsion Brouwer element out of something like this. Okay, what is the geometry that would actually explain some of these things? So I I've thought about it a little bit, not very much, but I have no idea how to do this. The geometry, the Hodge theory, this lattice stuff, is suggesting that one should be able to do this. Okay, and I would like to see it done. The whole point of having gone through this lattice theory is that, I mean, we didn't have a good source, a good way of scientifically trying to find these transcendental classes. This lattice theory is sort of telling us where to look, to actually sort of find these things and possibly write them down to study Brown-Manin obstructions. And I won't write it down, but let me just go over here and, well, let me put this back for the video. Okay, so here's one thing. These spaces, once P goes off to infinity, these spaces become general type. This is a famous theorem of Gritsenko, Hulink, and Sankaran. They're very high dimensional, but they become general type. And Sho Tanimoto and I are writing up a paper that says that the same is true for the moduli space of cubic fourfolds of discriminant D. You sort of import the techniques, but then you have to sort of jazz it all up to actually get it to work, and we get a precise bound. So for example, here, once this 2dp squared is bigger than 122, this thing becomes general type. I mean, we really know the moment when these things for sure are general type. Below that, there's some questions, a bit like with mg, above 24, you have general type, and then there's some region where you don't know, and then there's some region where it's unirational. So the same story is true here. Now these are gigantic, but if you take a lattice that's actually the Néron-Severi is a lot bigger, every time Néron-Severi gets bigger, these get smaller. Okay, and presumably they will remain general type as you sort of write these descriptions down. And we saw Lang's conjecture predicts that there aren't going to be that many rational points. Okay, so once these D's get really big, it's conceivable that these spaces are going to stop having rational points. I might have to take a big Néron-Severi lattice for that to be true. But then what that would imply is some sort of uniform boundedness for the kind of orders of transcendental elements that you might actually see. And that would be really interesting. The way I've stated it, it's probably a little bit hopeless with current technology, but it would be interesting to study in at least a few cases, say, for example, when the Picard rank is actually huge instead of tiny, and see if we can say anything. So that's basically most of what I want to say. I want to conclude by thanking you for being here. I've really enjoyed this. It's been a lot of fun. It was a lot of work too, but it was good. I came to the Arizona Winter School in 2005 for the first time. I realized this. This was 10 years ago, and I don't think I would have ever imagined when I was there that 10 years later I would be giving one of these lectures here. So it's been a real honor for me. So thank you very much.